in this lecture we will be solving Romanian Masters competition, problem number 6 from the year 2018. Here is a view of this problem. We are going to fix a circle gamma and a line L tangent to it, and then on the other side of the line from that circle we will draw another circle omega, but this one will be disjoint from L. That's important. So therefore we have two circles. One of the circles is tangent to L, the other one is disjoint from it, and from on that circle omega we will be picking a point x, a variable point, and we will draw two tangents from that point x to the point to the circle gamma, and we will have those two tangents intersect or cross the line L at y and z. Finally, we want, as x traces the circle omega, we would like to show that the circumcircle of triangle xyz is tangent to two fixed circles. It happens that these two circles are concentric circles, and our circle xyz is somehow squeezed between those two circles, as we will see in our solution next. So the problem says that we fix a circle gamma. Let's go ahead and start with that, and we want a line L tangent to gamma as well. So let's start with our circle. I will call the center of our circle, rename it as O, and the tangency point, probably I should call it as T. Let's go ahead and draw that tangent line as well. So there you go. I start, and I need a tangency here. I forgot to rename our circle. The problem clearly says the circle is gamma, so let's call it as gamma. Awesome. And this line is L, I believe. Yes. Rename it as L. Because I don't have an option to have a curly L, I just wrote it like this. Further, when you read the question, probably it might be a good idea to make the line look like horizontal. There you go. Finally, we are told to draw a new circle on the other side of our circle with respect to the line L. So let's go ahead and draw that other circle, which I will fix its radius. So let me put it right here, and let's call the radius as for example 2. How about that? Yeah, not bad. And that circle is called omega, so let's rename that circle as omega. Where is it? Omega, yes. So next we are told to pick a point on this circle omega, so let's go ahead and do that. There you go. And we call this point apparently as x. Rename it as x. There you are. And we draw tangents from that point x onto our line, onto our circle gamma, and you can clearly see the tangencies. And indeed, if I can just change the location of x as well. Next is, and those two tangent lines apparently they are called as f and g in this picture. Well, yeah. Okay. Next, we are told to label the intersection points here between L and the two tangents as y and z. So let me rename these as y and z. Rename as z. Awesome. So finally, maybe I need to make the label slightly larger. So just give me a second. So probably, I don't know, maybe 18? Yeah, 18 would be nice. Well, actually 18 is pretty large, so let's make it 16. Okay, good. Next is, well, the question says that the circumcircle of xyz will apparently be tangent to two fixed circles, and we need to find those two fixed circles. Alright, so let me go ahead and draw that circumcircle. So we want this circle to be tangent, so let's change its color, to be tangent to two circles. Let's see if we have such an impression. Yeah, maybe. Well, it's very hard to judge from now. For the time being, I don't need that circle. Actually, I will not need the circle at all. So for we see there's a lot of circles involved in this picture, right? So for that reason, I will be using an inversion, and you can follow from the official solution as well how inversion can be used to solve this problem. Okay, so my circle of inversion will be gamma. This will be my circle of inversion. So let's go ahead and invert everything with respect to gamma, with the exception of this red circle, which I will handle it in a minute. But let's go ahead and use the inversion icon here, so you can reflect about a circle. It's basically the same thing as inverting. So we can invert our circle omega with respect to gamma, and boom, here it is. We can reflect f with respect to our there you are, and in a similar way we can reflect the other tangent with respect to our circle, and boom. So it might be a good idea to reflect on what's going on. Let's for instance, yeah, so we can consider here, actually I wish oh, there you go, there you go. So this is a much better picture, because when the picture is too small, there's not much we can do. Maybe I can try to, yeah, so how about that? This is much better looking picture. Okay, what is this? I don't need well, okay. So the inverse of this line apparently is this circle, and this circle is named as G prime, so let me keep it here. And the inverse of this line, F, is F prime, so let me keep it here. Alright, so what I will do is, let me go ahead and draw different colors. So this line, let me make it green color. This one is, say, light blue. So therefore the light blue, this one will be light blue too, because it's inverted to that. And the green line is inverted to this one, so it should be green as well. There you are. And finally, if you want to do it, so you can label, this one is red, this one. So the pairs of inverses, I labeled them the same color. Next is, I'm curious about these points of interest. What will be the location? Oh, I forgot to invert this one. Okay, so our line, let's draw it as, I guess, orange. So our line L will be inverted into a circle. So let's go ahead and do that as well. So we invert this with respect to this. When you compare the green, the orange, and the blue circle, I think you guys all agree that they have the same radius, right? Because their diameter is exactly equal to the diameter, the radius of gamma, right? So gamma is our circle of inversion, and the radius of this circle happens to be the diameter of these three new circles, the green, the orange, and the blue one. Awesome. Now the points of interest. Let's use the inversion tool again. Where will y be inverted after inversion? Of course, because before inversion it's on the intersection of the blue and the orange line. After inversion it will go to the intersection of the blue and the orange circles, of course. And the same thing for z. After inversion it will go to the intersection of these two, which is z prime. Let's put the L prime here. Awesome. Now finally, how about x? Oops. No. The wrong one. So x will be inverted to, because through x you have three things going through, the green, the blue, the red. So the green, the blue, the red, it's right here. But let's see if inversion tells us the same thing. Yes, that's it. So now we see our triangle xyz inverted into x prime, y prime, z prime, because we wanted to show that the circumcircle of xyz is squeezed between two circles. Now the goal is to show that the circumcircle of x prime, y prime, z prime is squeezed between two circles. But before we do that, let's have a look into these lines. I want to have a look into these ones. So consider OZ prime, OY prime, and you just realize that the green circle is just a reflection of the orange circle with respect to OZ prime. Similarly, this blue circle is just a reflection of the orange circle again with respect to OY prime. Does that make sense? So therefore we have, so L prime, the inverse of this thing, L, line L, L prime, the orange circle, you reflect it across OZ prime, you get the green one. You reflect it across Y prime O, you get the blue one. Hey, that kind of gives us an idea to focus our attention on, on triangle OY prime Z prime. So look at this triangle OY prime Z prime. We have the circumcircle. We reflect across OZ prime one side. Hey, that circle it will go through the orthocenter. We know it very well. It's a very well-known property. The same way we reflect the circumcircle with respect to another side, this blue line will also go through that orthocenter. There's only one candidate, and it's x prime. X prime is indeed the orthocenter of our triangle. Let me go ahead and draw that altitude here. There you go. And I don't need to name that ray, so don't show me the label. But indeed, this angle here is 90 degrees, right? So this is an altitude indeed. So that's pretty cool. Okay, so, but as you can see, we are missing one circle. And what is that missing circle? Of course, if I reflect the orange circle one more time with respect to y prime, z prime, I get exactly the circle that I need, right? So let me actually do it. I want to reflect. Let's use the reflection tool probably. So let's reflect. Yeah, so we want to reflect across a line. We want to reflect this shape with respect to this, and boom. And guess what? This is x prime, y prime, z prime. This is exactly what we needed. Okay. Next, I want to focus my attention on two things. First is I want to label the center of this orange circle, which happens to be a very important circle apparently, as L. Let's go ahead and do that first. Rename as L. That's perfect. So that's the center of my orange circle. And I will also go ahead and locate the center here of this circle. Obviously, our circle of interest, the circumcircle of XYZ, and in line with the official solution, I will rename it as R. Now let's focus on some lengths. Well, before I do so, let me quickly remind you that let's see, the points L and R are just reflections of each other. That's exactly how we constructed our circle of interest, right? Actually, let's draw our circle of interest in purple color. So the purple circle is just a reflection of the orange circle. So the orange circle is the circumcircle of O, Y prime, Z prime, and its three reflections across the three sides gave rise to the green, the blue, and the purple circle. And it happened to be that the purple circle is the circumcircle of X prime, Y prime, Z prime. That's amazing. Okay, next is to have a look at some lengths here. Let's go ahead and 1, 2, 3, 4 maybe. Okay, so have a look at, oops, sorry for that. Have a look at this line. Actually, have a look at this shape. This. I claim that this is indeed a that's not a trapezoid. Not that one. Okay, sorry. Not that one. I meant to say this one. Sorry. Well, first let's consider this. Where is the reflection of O? O is on the orange circle, L prime. And of course, orange circle, when reflected across Y prime, Z prime, happens to be the purple circle. Because O is on the orange circle, after reflection, it will remain on the purple circle. So therefore, let's make it clear where it is. Okay, so therefore the reflection of O, actually let's just reflect it for God's sake, right? So we have this, and not surprisingly, it will be exactly on the purple circle, of course. So that's, yeah, let's call it O prime, I guess. Why not? Now let me finish drawing these lines. So I claim that this is a trapezoid. It's actually, well, obviously it's more than a trapezoid. It's an isosceles trapezoid. Let me quickly explain why. First of all, Y prime, Z prime is perpendicular to both LR, which are reflections of each other, and OO prime, which are again reflections of each other with respect to Y prime, Z prime. So therefore LR and OO prime are parallel to each other. Next, why is OL equal to RO prime? Oh, well, because it's reflections of each other. Again, it's an isosceles trapezoid. Okay, that's a silly question. Okay, now how about this one? RX prime. Do you guys see that O prime R X prime is an isosceles triangle? And as such, this angle here is equal to, let me draw the angle if you will, without labeling anything. So if you draw this angle here, R O prime, this angle, I don't know if you guys can see it, obviously it has the same measurement as this guy. Do you see that those two angles maybe? This little opening here, those angles, let me make them slightly larger and maybe with some decorations on it. Style, so let's increase the size and let's change the decoration. Let's do it like this, and we can do the same thing for the other one. Increase the size and the decoration, change it. Boom. So you guys can see why are these two equal, because of this isosceles triangle O prime R X prime. But remember that our trapezoid was isosceles as well, so we have this angle equal to that one as well. So O prime O L prime is also the same measurement, right? Because we have an isosceles trapezoid. So let's go ahead and increase the thing. Alrighty, so that's hey, that just suggests that O X prime R L is just a parallelogram. Do you guys see that? Because you have now X prime R is parallel to OL because of these corresponding angles, and earlier we have established that LR is parallel to O prime. Wow, so we have a parallelogram. Indeed, now it makes more and more sense. So look at that. So as I move X around my circle, that parallelogram does not change. Okay, now I no longer need the angles, so let me just remove the angles because it's giving me those silly shapes. Okay, do you guys see that? And because I don't need the other lines anymore, so I will just delete those lines. I really don't need them at all. So let's get rid of this guy and this guy in particular, and maybe if you wish we can reintroduce this part. But we have a parallelogram here for sure. Let's do it again. As I move X around my circle omega, the original circle, you have this weird shape going on. Does that make sense? Okay. Alright, so it looks like because L, O are fixed, do you guys see that? So all I'm doing as I circle around our original circle, this point X prime goes around the center of this circle, which I can label it as, say, let's call it B, I guess. Do you guys see that I am so my point of interest, this one X prime here, circles around omega prime around this circle B. But do you agree that the measurement, look at the measurement, it is just it is just, I can do the same operation. I can draw a little circle here around this point B, right? Does that make sense? So this is exactly what R traces. R traces a little circle, right? Does that make sense? So R is just tracing another circle. In fact, I can show you how it traces it, I guess. Oh, locus, yes. I want to find the locus of this point as I move this point. Okay, so let's around this. How does it work? Hold on. Oh, no. As I move the other one around that. Okay, sorry. Let's do it again. I want to find the location here with respect to this point. There you go. That's exactly what it is, right? So sure enough, as I move this guy, boom. And by the way, this is exactly the same size as this guy. Does that make sense? So it's exactly the same size. Okay, so this is the location of our centers. But by now you guys are already having an idea what will happen next, right? So let me just label it like dashed. Okay, good. Alright, so what I will do is I will just create this vector and then of the same size with this one, right? So let's go ahead and do that. Well, one way to do it is, let me do it the silly way. I will just draw a parallel line to this one going through this point, and I want to measure the distance Rx prime, a circle with that distance, Rx prime, boom. So therefore the point of interest is this point. So let's call this point N. I will call it as N, rename it as N. I claim that N is that special point and I no longer need these circles, neither this circle nor the line. Okay, boom. So therefore let's go ahead and draw our, so this line here is just parallel to the other line. So let me go ahead and show you what's going on. And look at what's happening here. Indeed, I can just get rid of some of the things I no longer need. For instance, this thing here and this one, I no longer need these, so let me, or at least I can do them dashed. And the same thing, why can't I select this guy? Oh, we have two segments, that's why. Okay, hold on. Segment LR. I don't need that one. How about now? Yes. Okay, I want to have this one dashed too. Okay, good. But I want to introduce a new line, a new one, this one, and this one. So this is a parallelogram for sure. Okay, let's check it. Oh, we have two parallelograms at the same time. Does that make sense? So we have this parallelogram here. That's perfect. Finally, what do I need? Oops. Actually, a lot of points I no longer need, so the picture looks complicated, but it's definitely not. So finally, the circle of interest would have a center here, and then radius equal to, well, the radius of gamma, right? So the gamma over 2, or maybe I should say L, okay, minus NR. So therefore, the little circle will be, okay, so let me draw that circle. So I'm interested in this circle, and then we can explain what is just happening. So center that N with radius, I think this one is bigger, so with radius OL minus, I don't know if GeoGebra will let me write it like that, OL minus NR. How about that? Would that happen? Oh yes, that's perfect. And then the other one, okay, perfect. And then the other one, another circle centered at N, except that it is plus this time, plus NR. Boom. Okay, now guys, let's long behold, so let's change the colors. I will make them light purple, and this one also light purple, and we're pretty much done with this question, right? So do you guys see that now as I move X around that circle, look how my thing goes around this. Okay, just a few reminders. These 2 points, let me show you something quickly. If I draw this line, that's exactly how I calculated the radius of these two circles. You can see that these are intersection points of the three objects here and here. So therefore, all the time, my circle, as I trace, let's go ahead and trace this circle. Do you see how C and D cover the whole thing? Does that make sense? So that's perfect. So therefore, for instance, at this stage, if you want to calculate the radius of that little circle, ND, the radius ND, it is just the radius RD minus the little radius, which is X prime B. That's what I did, or Rn. Does that make sense? And for the big circle, it is just NC is just RC, which is again the same circle L prime, so this one, plus NR this time. So minus NR plus NR, and we are done, right? Does that make sense? So as we are moving around this, look at this awesome picture. This is just a beauty. Hope you enjoyed it, and looking forward to see you guys in our next lecture.